Motivation. We want to describe, understand, and predict climate evolution, in other words, evaluation, okay, in a minimal way with maximum accuracy using to the fullest observational and computational advances. Data sources involve remote sensing observations and high-end computer simulations, both of increasing resolution and length. Methods involve nonlinear dynamic insights and statistical approximation and inference. So we want to develop methodology that can be applied across a broad range of time and space scales and test the methods on several distinct problems. Low frequency variability, LFV for friends of the large-scale mid-latitude atmosphere, and coupled ocean atmosphere variability in the tropical Pacific, and so were the ones which I meant to show you and probably won't have the time to do. Outline atmospheric LFV, what I call the waves versus particles in a PNAS paper, in other words, oscillatory versus episodic description. Concentration of variability along a ridge in the plane of wavelength and frequency. Oscillatory description, laboratory results, theoretical results about regime and bifurcation diagrams, which I think can be applied to GCMs with suitable emulators, etc., but I won't have the time to talk about that. Statistical results, spectral analysis for the oscillatory description, episodic description, weather regimes and their classification, Markov chains and long-range forecasting, LRF, and what's called today subseasonal to seasonal prediction. And so which one is better, waves or particles? And then finally about ENSO and artificial neural network learning, and so real-time forecast with singular spectral analysis, which I will have talked about in the context of oscillatory description, and empirical model reduction, and predicting critical transitions with an ANN model. And Coda concluding remarks on bibliography. Okay. So I was really glad to see that Pascal still calls the GCM a general circulation model rather than a global climate model. The acronym is the same, but the emphasis has shifted from trying to find out what the general circulation looks like to how it might change due to what the hell we're doing. So this is I would show things with a mouse, but I'm afraid to do the wrong thing on a PC and on a keypad. So anyhow, this is horizontal scale versus time scale. And a very important point is that there is a ridge of maximum variability which falls, roughly speaking, across along a diagonal in this plane, with convection and thunderstorms at the low end and sort of ENSO and other full planetary scale phenomena at the high end. And this is a really important thing which is totally non-trivial. If climate dynamics atmospheric dynamics were linear and commuted with a covariance operator the way things do in quantum mechanics, that's the way it should be. But it's nonlinear and very far from linearizations being self-adjoint, etc. Okay, so oscillatory description. Here is the Earth's atmosphere and the rotating differentially heated annulus. So basically, geophysical fluid dynamics, for those who come from informatics and not from climate, is essentially the large-scale dynamics of the atmosphere and oceans, which is characterized by the importance of rotation and stratification. And this has been reduced, has been put into a laboratory experiment doing his PhD thesis by Raymond Hyde, first published in 1953. And I'm proposing to you a review paper that we wrote on the occasion of Raymond's now deceased 80th birthday, which was celebrated at Oxford. So basically, this was the first time that such a regime diagram was done in geophysical fluid dynamics, and I think pretty much in fluid dynamics in general. And it shows essentially transitions. So the two axes are one that has to do with the rotation of this annulus, and the other one is usually called the thermal Rossby number, but should really be called the Hyde number. And within this regime diagram, you see you go from essentially no rotation, in which you simply have circulation like this. You would have what would correspond to two Hadley cells. As you start increasing the rotation, you get regular waves, purely periodic, and then you go on to vacillation, which is quasi-periodic, two independent frequencies, with either the shape of the wave or the amplitude changing, and then finally to a fuller spectrum and quasi-geostrophic turbulence. This is a simplified regime diagram, and basically Ed Lorentz in another paper in 1963, not the one that is usually cited, studied a truncated model of 14 ODEs in which he got something like what I'm showing here. And what I'm saying is that things like this can be done and should be done with GCMs via emulators, etc. You cannot have enough runs in order to do it with a full thing. But once you've produced a much simpler emulator, you can do these things. So this is just to give you an idea. This is out of Ed Lorentz's paper. This is the way visualization looked in 1963. You know, you just put points on a sheet of paper, and it is I who've added this tilted trough vacillation. So the index cycle represents meridional shifts of the mid-latitude westerlies along with their alternating strengthening and weakening. And Ed reproduced certain features of the tilted trough, also known as shape vacillation, in the annulus, and B, the latitude variations of the subtropical jet, but not the intensity variations. A comparison of the laboratory and theoretical results with the observations favor an oscillatory description understanding of the phenomenon. And I don't have the time to go into the, how you get exactly from periodic variability to irregular one, which might or might not be chaotic, but it could be chaotic plus stochastic. So this is just an artist's image of the spectrum of climatic variability, on which you see lines which are just the rotation of the Earth on its axis and its revolution around the sun. And then most of the variability is in this continuous background, but there are these bumps which to me look like the product of broadening of lines that were produced by Hopf bifurcations. And that is one way of thinking about everything in this regime diagram. And it's very interesting that in a paper of Murray Mitchell in Quaternary Science Review in 1976, the same year as Hasselmann's famous 1976 paper in Tellus, there was this phrase, this is taken from an article of mine in the Encyclopedia of Global Environmental Change, is this phrase, no known source of deterministic internal variability. So 76 was one year after my PhD, and my sort of adult life has been dedicated to destroying this silly sentence. Okay? So what is a connection to spectral analysis? The connection to spectral analysis is that you have what's sometimes called simply unstable periodic orbits, and I call in quotation marks stable limit cycles. In the phase space of the system, you have something which is a periodic orbit, but which is stable in many, many directions. Okay, incidentally, that's a Poincaré section of Poincaré map. And there's just one or two or just a very few directions of instability, so orbits or trajectories in phase space sort of go around, and they get close to this and turn a few times around, and then they wander away. And each time they turn around, if I had a blackboard and time, I would just show you, each time they turn they deposit in the time series something that will be picked up by advanced spectral methods. Okay? So some of you know this already. So basically, you've heard about empirical orthogonal functions. So on the left, you have spatial EOFs, the decomposition into separation of variables between time and space. And this is done following Kahunen and Loev in 48 and 49 by diagonalizing the covariance operator or the covariance matrix, if you prefer. And the counterpart on the time is you look at the time series. There's a typo in this. It's some time series capital X of t plus s. So on the left, the separation was between variables that have different units, time and space. Here it is just between time and lag, which have the same units, but everything else works the same. And then in a so-called scree diagram of the singular values of this decomposition versus the order, you will have pairs which are the nonlinear counterpart of sines and cosines. And I'm going to show you the video refers to a multi-channel generalization of this, which is pretty spectacular in terms of interpreting results of both large observational data sets and simulations. Full model simulation. So this is the math of it, and I would have explained it to you if I hadn't done this, at 2 a.m. and not remembered the name of the damn folder. Apologies once again. So this is essentially how this decomposition works. Up there, you have Nino 3, which is one of the indices of the El Nino for 1950 to 2000. And this is a leading pair of temporal EOFs. And then there's a partial reconstruction of the periodic components, which looks like the lower panel. Okay? And we've been doing real-time forecasting of ENSO, first within what was called the Experimental Long Lead Forecast Bulletin of the Climate Analysis Center at NMC at the time, and now at the IRI, the International Research Institute for Climate and Society, the well-known forecast plume. So you have something like, at the time when I did this slide, but it hasn't changed that much, about a dozen big models and about half a dozen small models, statistical ones. And basically, the last time that the revision of the skill at forecasting was done by Tony Barnson at Associates in 2012, it said that since we've changed from SSA to this other method that I don't have the time to discuss with you, empirical model reduction, that this, it is shown, the red points there, the UCLA TCD stands for my research group, Theoretical Climate Dynamics. And so they said the EMI ENSO model has a higher seasonally combined correlation skill among the statistical models, exceeded by only a few dynamical models. Okay, so Pascal said that many of the models in the CMIP and assessment reports still don't do a great ENSO, and statistical. But again, I want to emphasize that these statistical models are informed by a dynamical understanding of what the heck is going on. Okay, so episodic description, weather regimes and their classification. Markov chains and long-range forecasting, which one is better, waves versus particles? Okay, so blocking, a paradigm of what's called persistence anomalies of the large-scale atmospheric circulation. This goes back to just before World War II. Bauer and Namias, whom I mentioned already, and Rex. Many others noticed recurrence of and persistence of blocking. So what is blocking? Normally the westerlies flow around parallel to circles of latitude or zonally, but then you have bumps like this. This just happens. You happen to have West Coast blocking coincide with Atlantic blocking, which is very rarely the case. And so these block the westerlies, hence a known blocking, and they can last for longer. Low frequency you always have to define with respect to what. Low frequency is with respect to the life cycle of synoptic eddies or weather systems, which is say 5 to 7 days. These can last 10 days and a month. Okay? So Jules Charney, as he once told me, we used to meet at NASA's Goddard Space Flight Center. He said, everybody is talking about this horse shit, so somebody's got to do something about it, okay? So he wrote the famous Charney and DeVore paper, and sort of modern studies of blocking have taken off from there. This is a bifurcation diagram, and here are the flow patterns associated with zonal flow, which is not perfectly zonal, but is in phase with the topography, the simplified topography of the model, and the lower one is a blocked flow where it's shifted with respect to upstream with respect to the topography. Okay, so this is again from an experimental paper with the research group of Harry Sweeney. And this is just an illustration taken out of the work of the observation analysis work of my student Masa Kimoto, now a full professor at the University of Tokyo. So again, on the left, you have a 10 days out of the life of the atmosphere, which are zonal. And on the right, again, you have this such a double block. And so in the experiment, this was now not the so-called differentially heated annulus, but the barotropic annulus at Harry Sweeney, and actually not Ghil Sommeria, but sorry. The other Sommeria did his postdoc with him, they built. And so I suggested putting mountains into them. And we reproduced this bistability between blocked and zonal. And as a matter of fact, the duration of the relative duration of blocked and zonal events in this intermittent time series is plotted in the lower panel, and it corresponds very well to the theoretical results published in JAZZ out of Bernard Legras' PhD thesis. So the idea is from regimes now to Markov chains. Each regime has an expected duration and an expected transition probability from regime A to B, and transitions do not occur via the mean state. The mean state is just a statistical accident. It is something that doesn't happen particularly often, or maybe the root of the bifurcation tree, which is a little bit more complicated. So all of this is schematized in this contribution to a paper on nonlinearity in a book from a summer school on nonlinearity in the geosciences by Cathy and Grégoire Nicolis. So this is, again, just a courtesy of Tim Palmer, who at the time was still at the European Center for Medium-Range Weather Forecast. It's a famous Christmas storm that blew the roof off Olivier's office next to mine, okay? And so up there is a deterministic prediction and the verification, which are quite different. And you see these are the 50 members of the ensemble. And you see that there's essentially, this is now not blocking, but you still clearly have what's called coarse graining of the phase space. There's not simply exponential divergence, but there's a tendency, some of these occurrences are actually deeper lows than the one that was actually observed. Okay, so this is now out of a contribution of Lenny Smith to the Encyclopedia of Atmospheric Sciences. So it's just the evolution of the PDF in the Lorentz 1963 convection model that starts out here and then bifurcates between the two wings of the butterfly. And so again, you don't just have exponential divergence, you have coarse graining of the phase space. Okay, so how to get from a regime to another? So this is a particular Shilnikov type orbit, which is associated with a particular kind of bifurcations. So it can, but basically Charney and the Charney-DeVoy papers suggests a stochastic bifurcation. So it can be a heteroclinic or homoclinic orbit. This is homoclinic, comes back to where it started out. So, in more general cases, as I said, there would be maybe a couple of unstable directions, and this plane would be the whole rest of the phase space, including infinity. So chaotic itinerancy, Kimoto and Ito, or all of the above. Okay, so this is just to show you that there are, I don't know how many different classification schemes of the regimes, and then also studies of transition probabilities, etc. So there's a rich literature and all this stuff. And it involves also the fact that actually the phase space of the atmosphere is pretty complicated because there is chaotic stuff, and stochastic perturbations do smooth it or not. Okay, and basically we have also studied first in an intermediate model, so-called what they call the QG3 model, because it had 3 levels of Marshall and Molteni, and then in actual northern hemisphere reanalysis, the best parameters for estimating transitions from between zonal and blocked and other kinds of flow. Again, because to this day, even the best, the top of the line numerical weather prediction model, European Center, JMA, NCIP, etc., do not do a good job job of the frequency and amplitude. And once you're in a blocking situation, they keep it going, but they are not very good at the transitions. And so this is just a summary of waves versus particles. So there are all these ways that you can think about it. You can think about these persistent anomalies as just being slow phases of limit cycle. So it can be zonal and blocked, or PNA, RNA, and blocked NAO, the negative phase of the NAO, as in this observational study, or are they just oscillations, the oscillations but instabilities of particular equilibria? That's the way it looked in the Ghil paper. How about chaotic itinerancy, Ito and Kimoto? How about neither? So, Dick Lindzen, who not only doesn't believe in global warming, he also doesn't believe in nonlinearity. So the idea is just that it's some interference of linear waves, neutrally stable Rossby waves. Okay, so I'm coming to an actual application of neural networks. AAN just stands so that you can read the algorithm. Artificial neural networks are not the ones that we're actually using in our brain. Real-time forecast with SSA and EMR, and predicting critical transitions with an ANN model. So again, I don't have the time to show you exactly how we did those real-time forecasts, except I showed you the success as estimated by the authority, that shepherds the ENSO forecast plume. So just in case anybody is here who doesn't know about ENSO yet, so it's basically a phenomenon associated with coupling of the ocean and the atmosphere in the tropical Pacific. And you can find this on the web and read up on it, in particular on the IRI site. So not only does it dominate interannual climate variability globally via teleconnections, actually there's a very interesting question, because the tropical Pacific, depending exactly how you define tropical, it can be as much as 1/3 of the surface of the globe. So when you have a strong El Nino, the mean temperature of the globe is higher. So it's one of the hardest issues in disentangling intrinsic variability from forced variability, okay? Because it's not clear whether it's the global temperature that affects El Nino or just the El Nino which manifests itself in the global temperature that you're measuring, okay? So intrinsic variability interacts with seasonal forcing and leads to irregular occurrences of large climate anomalies. Okay, our success in predicting has essentially to do with the fact that the large events are just positive interferences with the quasi-biennial and the quasi-quadrennial or low frequency component of ENSO. So again, these are two scalar time series. I mentioned already Nino 3, which is sea surface temperatures, and the other one is this SOI, the Southern Oscillation Index, discovered by Sir Gilbert Walker, which has to do with sea level seesaw between Darwin and Tahiti. Today it used to be Batavia, now Jakarta and Tahiti. And Tahiti is actually not terribly good because it's not on the equator, but it's the best you got because you don't really have measurements on the Galapagos Islands where you should have put them. Okay, but now the point is that these things are so highly anti-correlated that anybody who tells me that there isn't, there were attempts at some point when deterministic chaos became popular to say that the climate system is actually low dimensional. You can get, there are various methods, Garsberger, Procaccia, and many others, for determining the fractional dimension of a dynamical system, and there were claims like that, but that's of course baloney because it's not low dimensional in any real sense. But this clearly shows that there's a lot of the variance in something very large scale. You cannot get this anti-correlation without that being the case. So let's just say that we believe that there's something important in the leading order components of the phenomenon. So some very simple models were developed, so-called differential delay equation models of ENSO variability, starting with Battisti and Hurst, and then Suarez and Schopp, and finally Eli Zipperman and colleagues. So This was first published in the same issue of Science in 1994, in which Fei-Fei Jin, David Nealon, and myself also had a paper on this, on the quasi-periodicity and the Devil's Staircase route to chaos. So coming to why in the world you would be able to do anything with a neural network, there's an actual theorem by Shekroon, lead author, Nealon, Kondrashov, McWilliams, and myself, in this paper that you'll find in the references at the end of the talk, which says essentially that you can, under certain suitable mathematical conditions, which you cannot, of course, test on the atmosphere itself, and not even on the GCM, but you can sort of, you have reasons to believe, you can represent a higher, high-dimensional dynamics in continuous time by a Markov chain of finite and not very large order. And so I'm just illustrating here. There were two papers written with a group of researchers in Nizhny Novgorod at the institute, essentially, that Andronov, of the famous Andronov and Pontryagin paper on système grossier, you know, on robustness of dynamical systems, founded in the 30s. Okay, so we model ENSO simulations by delay differential DDE models and then intermediate coupled models using artificial neural networks, okay? So it's not really, at this stage, it's not really the observations, it's simulations. In the first part, it's a two-part paper. In the first part on a DDE model like the one that I showed you, and in the second part, an intermediate coupled model with essentially this Jin, Nealon, Ghil model, okay? And so DNS are based on the Markov chain representation theorem. Oh, below I meant to switch the order of the slides, but it's above now. They include a deterministic part F with dimension D and M sub F parameters, and the stochastic part G, so that's a matrix with MG parameters, and zeta n is noise, okay? So the upper panel is Galanti and Zipperman. That's yet another ENSO model, delay differential ENSO model by Elliot Zipperman and one of his PhD students. So you can do 9,000 years easily. Okay, so that's in red with the training interval in black. Now, please do observe that there are transitions, but they are not in the training period. Okay, so lower panel is the A and M behavior with D equal 2, MF equal 12, and MG equal 2, so that's blue. And you see that in this case, really, the DD model is highly idealized, but still infinitely dimensional, because you have to give initial data over the entire length of the delay. So in Mark 2, the training interval did not include the DD's model second regime. So I find this pretty amazing, and I don't understand it yet. So I'm just showing you. I hope that one of you will explain it to me. Okay? So now part 2, we use this intermediate coupled model of Jin, Nealon, and Ghil. So as I said, it was first in the same issue of Science as Zipperman et al., and then in greater detail in Physica D 2 years later, which has explicit space dependence on longitude along the equator, and exhibits a Devil's Staircase due to interaction of seasonal cycle with the model's intrinsic oscillation. So the ICM simulation is analyzed by multi-channel SSA, which I hinted at earlier. And we keep the 6 leading so-called spatiotemporal PCs, which capture just over 60% of the total variance. So it is these that are used in the ANN. So again, the upper panel shows the model simulation of 15,000 years in red, and with a training interval which is 4,000 years long. Now it has a small piece of the other regime, okay? And again, the ANN model behavior, so they do not occur exactly at the right times, but there's something there, okay? So first of all, the projection onto the leading STOFs was very useful, because if you only projected on the usual spatial EOFs, the results were much poorer. I don't have the time to show you that, okay? And in Mark 2, several critical transitions occur, but the timing is not quite accurate. But as they say in the United States, good enough for government work. Those who are US people here, no. Okay, concluding remarks and bibliography. Okay, so fairly sophisticated methods of statistical approximation and inference have been developed over the last few decades in the climate sciences. They've been used to describe, understand, and predict, in certain cases in real time, climate phenomena on various time scales. So I just gave you basically 2 examples, but many more. Connections with and understanding the underlying nonlinear dynamics has been a key ingredient of these advances. So, you know, I think that's silly not to use dynamics in the way that you devise your statistical inference models. And just to give you an idea of another scale, the original paper on SSA with Robert Votard was written in the context of paleoclimate studies, okay? So great strides in computer-powered observing systems can clearly help achieve further progress. So I didn't pronounce till this point in time the words big data, but clearly the data are getting bigger and bigger. Okay, so we better do something with them. And so this is just the bibliography, and I will now show you the video. Okay, so sorry, this is your.
It's yours, so it should be in the folder.
Okay, it's in the moniteur de type inconnu. I don't know what the hell. Oh, okay.
Yeah.
Okay, so sorry. There's it wants. Il faut juste annuler. Okay, great. Okay, thanks. The master of the clocks, you know. Okay, so. Okay, so wait a second. I need to magnify this. So this is the analysis. The upper part is wind stress, and the lower part is SSTs taken from reanalysis. One is the COATS, and the other one is some European Center reanalysis. Sorry, as I should have looked this up again, but it's in the Groth et al. Paper. It's supplementary information for a Groth et al. Paper in the Journal of Climate, published, I think, in 2 years ago, in 2017. So the point of there are 2 points. One is that it clearly shows intrinsic ocean variability. So this extracts the mode which has a periodicity of 7.6 years. So this corresponds to, you know, the middle of one of those bumps in the idealized diagram on climate variability. There's a 7 to 8 year periodicity in the NAO. And so it is, first of all, it shows that in its current version, multi-channel SSA can analyze that it's no longer necessary to project onto the leading EOFs, spatial EOFs. So you can see very small scale features, while the wind stress is basically a north-south seesaw of very large scales. Okay? So I'm just showing you 2 cycles. Okay? So you see, in particular, this variability is concentrated in the Gulf Stream and the North Atlantic drift. The extension of the Gulf Stream in a way that was predicted in theoretical papers with successive detail and coupling to the atmosphere, etc., starting with a paper with Shi Zhang and Feifei Jin, myself in JPO, Journal of Physical Oceanography, in 1995. So it's totally consistent with that, but in any case, it also shows the power of the method, which now can analyze full data sets without previous production to much lower spatial resolution. Okay, so I will go back to the this. Okay. And thank you very much for having given me the time. Okay.
Thank you very much for this very
Again,
interesting
apologies
talk.
for having had to go that fast, but I'm available. Actually, this, I will have to go back to my office at some point, but I will be here in the afternoon.
Great.
So I can't go to lunch, have fun. You'll see how the students at the École Normale, who don't just get a fellowship, but they're actually what's called civil servants in training. So they have a real salary, and on top of that, they get good meals.
But we actually still have 15 minutes, 10 minutes time to get into discussions.
No.
So yeah, I'm opening the floor for questions.
So Michael, thank you very much for the nice talk. So the question is, so we've seen about when we try to understand the present climate system that we need high enough resolution. With 1 degree, we can simulate more or less what the ocean is doing, but to understand mechanistically what it does, to understand how things are connected, we need higher resolution than, let's say, 1 degree. And of course, when we run these big climate models forward in time, then often they have lower resolution. So I was wondering what's your view on this, right? If we want, do we want to simulate things, and if we want to understand them, then we need high resolution. Your last, I missed actually the point of your last slide.
Point well taken.
Yeah.
First of all, actually, in a paper with Itzhak Felix and Eric Simonet in JAZ in 2007, first 2004 in a barotropic model, then 2007, we did show, you see, the issue of the impact of SST anomalies on the atmosphere in SST anomalies in mid-latitudes has been a very controversial one for a couple decades. And we showed explicitly, again, by using this simple model in which we could increase or decrease resolution at will, that the reason that controversy persisted is because GCMs that were used in climate studies had resolutions that were 100 to 200 kilometers at best, and you needed less than 50 kilometers in order for the atmosphere to feel what the Gulf Stream does. Okay, so but my position on this has been very clear for, again, more decades than I care to count. You need the full hierarchy of models. Some people even have graphs in which they show that detail moves to the right and understanding moves to the left. Okay, so on the other hand, clearly you cannot, while low order models and other idealized models can produce qualitative results, in order to have quantitative comparisons, you need the higher resolution. So, I have another slide that I show very often, but I haven't shown here, in which, of motivation, in which I put toy models and conceptual in parentheses, and on the other hand, realistic in quotation marks and detailed in parentheses. This warring between people who push the resolution and people who try to push the understanding has to cease, and we should talk to each other, But it's a little bit difficult because with all the attention given to the IPCC, excuse those who participate at great cost to their time and families in it, has led to the fact that even the 10% that the more theoretical research would need to flourish are not granted any longer. Fundamental research is suffering from the interest in climate. It is not gaining from it. Sorry.
Michael, thank you for the talk. There was, in the end, you were saying that you used an artificial neural network in order to predict some of the behaviors, but you have said that this allowed to use bigger models and not used to. It is not. We don't need as much to use smaller reduced models. But isn't the artificial network then doing the work of reducing the information of the bigger model in some way?
Well, everything within reason. In other words, I do believe that adding a few layers to a neural network can do wonders if you have enough data to tune the coefficients, okay? But I think that the idea that we're going to replace GCMs by deep learning, okay, where depth is counted in the number of layers, okay, not in the depth of the thinking about it, is somewhat of an illusion. Okay, I really believe that statistics. There's a very simple trade-off in statistics. Okay, between the number of parameters that you're trying to estimate and the reliability of the estimate. Okay, so if you are trying to replace a GCM, and you think that you are going to have, 10 to the whatever 7 nodes, okay, and be able to train them. The huge amount of data that we have from satellites, etc., are not necessarily independent data. Okay, so I think that this is, in German it's called ein Holzweg. It's not not the right path. So I think that yes, stochastic, you can replace parameterizations in a GCM by doing neural networks, and I've already seen papers that claim to have done that successfully. I haven't read them yet. So, but the idea that you are going to replace a whole GCM by a neural network is, excuse me, it's a little bit like those papers that when deterministic chaos became fashionable, we're trying to demonstrate that the climate system is, 2.7 dimensional. Okay?
Further questions? We have 5 more minutes. Yeah.
Thanks for the talk. So I have a question for the SSA. Because in the machine learning literature there is now a lot of work on nonlinear dimension reduction, and I wonder for a system as complex as nature, where there is a lot of nonlinearity, what's the impact of imposing the orthogonality in the EOFs and then the SSA PCs?
Well, there are various, I think there's a gentleman by the name of Shea who has published a paper on nonlinear SSA, etc. The point is that while there are many things that are good about linearity. One is that you understand it, and but while of course diagonalizing a matrix is basically something that has to do with linear algebra, the fact that the EOFs can be anharmonic, okay. You see, if you have something that's purely periodic, but it's a sawtooth, okay, it goes like this. You need a lot of Fourier components, okay. That's why this is more parsimonious, okay. Now, frankly, I have not seen any result by any of these other methods that we couldn't get with SSA, or that we hadn't gotten with SSA. Okay. Now, I'm not claiming that it's a cure-all. There are people who go around and think that their method is doing everything. One of them is Dave Thompson with the multi-taper method. Okay. It gave him a good life because he could do what he wanted in his research after saving Bell Labs from some snafu in hardware. But there are problems with that, and SSA is very good at amplitude modulation in ways that other spectral methods are not, and it is not good at frequency modulation. On the other hand, you show the wavelet spectrum, and my problem, in spite of that famous curve with wavelet spectra, is that you are trying to get the 2-dimensional information out of a 1-dimensional time series. So again, it's clearly trying to do too much. And I've used wavelets, and I've used multi-taper and so on, and we try to compare things and so on. So I think it's still pretty good. Again, good enough for government work.
Thanks. We still have 3 more minutes.
C'est bon.
Anyone? I have a question. Like you mentioned that when you use and build machine learning or statistical models, that the dynamics are very important to integrate. And can you give an advice on which part of the dynamics or how they can be addressed?
When I will fully understand this two-part paper that I showed you, I'll have better advice. But on the face of it, you see, on one of the things about SSA, unlike you know, empirical mode decomposition of Cecile Plendeland, who actually was my postdoc, and we even wrote a paper together, you know, it gives you the dynamics, okay? It gives you explicitly the dynamics. SSA doesn't, but I do have an idea of how to do that, okay? In any case, you know, it's conceptually linked to the fact that you have a Hopf bifurcation somewhere behind you in the bifurcation tree, and you can still see it in this broad peak. But as I say, I think that I've seen in the program, somebody is going to talk about hybrid methods. So again, to the extent that you would do you know, deep learning-based parameterizations in a GCM, I think that that's one answer. Okay, that's obvious, that you can do modules which are in some sense more compact than the whole problem. But you see, what stares you in the face is that there's no understanding. I mean, you know, it's clear that machine learning works very well on pattern recognition. I mean, honestly, when I saw the first time on Google, you know, the fact that they offered images to recognize, I said, baloney. Well, it works pretty well. But again, it's a fairly simple problem, in quotation marks, especially since it's solved.